ladies and gentlemen, to this webinar about ventilative cooling. And my name is Yannick Roth, and I work for WindowMaster. And with me here today is Professor Per Heiselberg from Aalborg University, who will give a lecture in ventilative cooling and its application and etc. Yes, but before we start, I have some practical information. I think we have checked the sound, and that should be fairly okay. I hope so. And this webinar is scheduled for approximately 1 hour, so I think we will have around 45 minutes of presentation, and afterwards we will also have a Q&A session. And the question, you can ask them in the chat box area, as you already have done with a yes. So here you are also welcome to ask us questions if you have some. And of course we will try to answer as many questions along the presentation as we go. So if you have any questions during the presentation, you are also welcome to write them or give them to us. And some of them we can answer during the presentation, and some of them we might save for later to the Q&A session in the end. Yeah, and here are some tips and tricks. So if you have bad connection, please close all other applications on your computer. And also it's much better to be on a wired internet connection compared to a Wi-Fi connection. Okay, so that was just some practical information here. So the agenda is quite simple and short. So Per will start tell you about ventilative cooling, and then afterwards I will give you some insights in some of our case studies we have done, and lastly we will take the Q&A session. So I will give the microphone to Per Heiselberg. I will just switch this presentation, and here comes Per's presentation here. Hopefully you can all see that just in a moment. Yes, I'm pleased and delighted to give the microphone to Per Heiselberg. Here you go, Per.
Thank you, Yannick. Welcome to this presentation about ventilative cooling. I will give you a short background of why we see an increase in the interest of ventilated cooling, as well as say something about the potentials and limitations, give a short overview of what are the principles we are working with, and give a very few examples to illustrate the principles, and then Yannick will afterward give some more elaborated examples. First, why do we see an increased interest in ventilated cooling? It's mainly because we can see that overheating is becoming a larger problem in buildings, especially in new low-energy buildings, but actually also in connection to renovations. We have in these years a lot of focus on decreasing the energy use, and in many, especially in the North European countries, we are not so used to focus on cooling, so it's often underestimated in the design process. Secondly, the methodologies we are using to evaluate energy use in buildings we have are often too simplified. We are maybe averaging heat loads in time and space, and and therefore underestimating the issue. I will show you short examples of what can happen. This is an example of 4 residential buildings which were renovated in Denmark, which was renovated to different degrees. This table here shows some ideas about that some windows, only windows were changed, other windows also insulation in the ceiling and in the floor, and then finally also another building was completely renovated with change of also the building envelope. However, if you see on the results of the thermal conditions in these buildings, we can see that especially one building had a very big problem with overheating. It was not the building which has the most extensive renovation. It was just a selection of measures that was handled, while the building which was actually extensively renovated with you could say a lot of measures and also achieved a lower energy consumption in total, actually had much less overheating problems. So it's not a question of the degree of renovation, if you could say, or the level of energy used, but it's more a question about how is the building designed, and what is the relation between the heat load from the sun and the thermal loss from the building. But this is an example of a project being done without taking into consideration that overheating could become a problem. Then another reason, as I see it, why we see more challenges with overheating is because the technologies we are using is changing. In many years, we have concentrated on increasing the insulation in the envelope, improving air tightness, maybe improving ventilation heat recovery. And all these technologies are very robust to the interaction of users. But when we look at new buildings and renovations today, we are also taking other measures to reach the ambitious energy goals of the buildings, like demand control ventilation, maybe solar shading, lighting control, assuming window opening in the summertime. And all these technologies, their performance is very sensitive to control, and they involve, you could say, a degree of user interaction. And some of them are actually also difficult for users to understand. So this means that even though we have implemented technologies in the building, they might not be used as expected or as we want them to be used, and this can also cause problems. Here I have another example. It's actually a quite old example from one of the first zero energy buildings in Denmark. Here we see, I think for the first year of running this building, we see a curve showing the operative temperature as a function of the outdoor running mean temperature. And what you can identify here is that all the blue dots are in the winter period and all the orange ones are in the summer period. And you can actually see that during the winter time, there are many incidents with quite high temperatures. Of course, in this building is equipped with solar shading and possibilities to open windows to cool down the building. But looking at the use of these technologies, we can see that they are not used actually to keep the temperature down. This figure shows the green dots shows when windows are opened, and the red dots when windows are closed. And even though we have temperatures which are very high, we can also see that these are actually not the incidents where the windows are opened, even if the outdoor temperature could be quite cool. The same tendency we can see with the solar shading, where this figure shows with green dots when solar shading is activated, and the red dots when it's not activated. And we can also see here that there is not a clear correlation between high temperatures and activation of the solar shading. So users do not, you could say, activate the system to reduce temperature, but they maybe activate the system to ensure privacy or to avoid glare or to get some fresh air. So we have a challenge, you could say, to educate people to use, it's not new technologies, but to use technologies to fulfill the goals they have for the indoor environment. The reason we focus very much on ventilative cooling is because ventilation is already present in buildings. And if we use the outdoor air to remove the heat, it has a high cooling potential. as I also illustrated with the previous building examples, it's not only in the peak summer week that we have a need for cooling. We actually have a need for cooling more or less all the year round. This also goes for office buildings. So this means we have a possibility to use this potential in a large part of the year, or this free cooling potential of the outdoor air temperature in a large part of the year. The way we define ventilative cooling is we say it's application of ventilation where we use the outdoor airflow to reduce the cooling load in buildings. And we actually, and for these systems, they can be driven both by natural driving forces or mechanical driving forces, or it can be a combination of driving forces. If we look into the potential limitations, as I said before, we have a cooling need most of the year. So this means the outdoor temperature is often lower than the thermal comfort limits we have in our buildings. Especially during night, these temperatures are below comfort limits, so give a good potential also for night cooling. But of course, we also have some limitations. Sometime in the future or in the next years, it seems that the temperatures are steadily increasing. So this means that the large potential we have today is maybe smaller, will be smaller in the future. And it's also clear that if we have peak summer conditions with very high temperatures or periods with high humidity, that it is difficult to use the outdoor air for cooling. The location of the building is also important. In urban locations, the cooling potential might be reduced because of heat island effects. It might also be difficult to use natural driving forces because of the higher temperatures or the lower wind speeds, and as well noise and pollution can be conditions that can make it more difficult to use the outdoor air directly for cooling. If we look into mechanical systems, of course the energy used for air transport limits the potential, so you might save energy on cooling, but if you use a similar amount of energy for air transport, then in total you have not saved very much. So for mechanical systems, it's important to have low energy use for air transport to make ventilative cooling successful. And for the natural systems, we have for ventilated cooling, we have the same challenges as for natural ventilation, that the building design and the different fire regulations and security issues and so on are also decreasing the potential for ventilative cooling. This table gives an overview of you could say the way we divide ventilated cooling into different principles. On the left hand side, you see the outdoor temperature or the daytime mean outdoor temperature. So it can be cold, or it can be temperate, it can be hot and dry, or it can be hot and humid. And on the top you see different solutions for ventilation systems, either driven by natural forces, by a combination of natural and mechanical forces, or by mechanical forces. And then if you look in the table, you could see our suggestion to, you could say, apply different types of systems depending on the outdoor temperature. So if you have a cold environment and you have a natural driving force, then of course you should minimize the airflow rate and ensure to have a drought-free air supply. If you have a mechanical system, you have a possibility to apply a heat recovery to increase the supply air temperature, and in that way provide a drought-free air supply. It might or it will cause you to that you would have to use a higher airflow rate, because when you use heat recovery, you reduce the cooling potential. So this means you need to have additional airflow. Similar, you could see a situation here. For example, if you have a hot and dry period, then you should, for a natural system, use a minimum airflow rate during daytime, and you should maximize the airflow rate during nighttime. Same is the condition with mechanical systems, that you should exploit the cooling potential that is largest in the nighttime. And if you have a hot and humid conditions, well, you cannot use the outdoor air directly for cooling. So this means if in hot and humid conditions, you need to have some mechanical cooling and dehumidification to fulfill the indoor requirements. I will now give you some examples of, you could say, solutions that fit into this picture. And I will start with looking at a situation where we have cold outdoor conditions and we use mechanical ventilation to provide the cooling. And this is an example of an office building where we have a special system to supply the air. We supply the air through directly through the ceiling. So we have some diffused panels to supply air, and actually here we have the extract of air from the space. And so in principle it looks like this, that we supply air to the plenum, and then it's distributed to the room through the perforated ceiling panels. We have an exhaust airflow from the room, and we actually also have a fan coil unit in the plenum, so we can add additional cooling or heating to the space if it's necessary. The advantage of this system is that we can provide very cold outside air, so this means we can decrease the airflow rate needed to cool down to the building, actually to the what is needed for indoor air quality, so we can reduce the energy use for the fan or for the transport of energy. And the advantage of using these diffuse ceiling panels is that we can actually provide air to the space very comfortably, even though we have a low temperature. So in this case, for example, I just need the green one there. We can supply air with a temperature of -8 degrees directly to the plenum, and then supply it to the space without creating any draft for the occupants sitting there. Another example is, you could say, natural ventilation, where we increase the flow rate if you have a temperate conditions to cool down the building. And there I have an example that one of our PhD students have done lately, looking into a renovated residence and how you can use natural ventilation to ensure comfortable conditions during summertime. So this was the case, especially looking at the first floor and the sleeping rooms on the first floor, and comparing, you could say, 2 summers. One was 2015, where the ventilation was done by a constant mechanical ventilation for the building, and then you could say manual use of roof windows and solar shading as the users find best. And then in the summer of 2016, the mechanical ventilation system was shut down, and instead an automatic opening system for the windows and an automatic system for the solar shading on the windows was introduced. And the results of that showed that actually in the summer of 15, where the mechanical system was running, that we actually had quite a lot of hours with high temperatures, almost 100 hours in some rooms above 28 degrees, and almost 200 hours above 27 degrees, while in the summer of 16, where we had comparable temperatures, using the natural ventilation could ensure much lower temperatures. And of course, the main reason for this is that the mechanical ventilation system is designed for indoor air quality, and the capacity is too low to efficiently cool down the building. The last one I will say something about is the airflow rate, you could say during daytime, or more or less the use of nighttime cooling. And what I mean by maximum airflow rate during nighttime cooling. There I don't have of course the example before was also with nighttime cooling, but I have some simulations to illustrate the importance of having a high airflow rate to make an efficient nighttime cooling. So this is a study example with a typical office room where a sensitivity study was made looking into what is the impact of the thermal mass of the building construction, what is the impact of how large the heat gain is on the temperature in the space, and then it was done for a Swiss climate where we have relatively high summer temperatures. We had implemented a nighttime ventilation in the basic case with an air change rate of 6 air changes per hour, and it was running from 7 in the evening to 7 in the morning if the temperature difference between the room and outside was more than 3 degrees. And then we stop when the surface temperature come below 20 degrees. So, and here's the results, and the conclusion here is that if you have, you could say, a lightweight, if night ventilation should be efficient, it actually requires that you have enough thermal mass in the building to store the daytime excess heat, to be able to release it during nighttime. So if you have medium or high heat gains, it's also necessary to have high thermal masses to be able to store the heat. And then you can remove it efficiently by the nighttime ventilation. If you do not have enough thermal mass, it's very difficult, even if you have an efficient nighttime system, to ensure that temperatures do not become too high during daytime. Then another important example which is shown by these figures is how much air is actually needed to ensure an efficient night cooling. So on the figures here you can see the number of hours above 26 degrees in the space, and as a function of the air change rate during nighttime ventilation. And you can see if you have very low heat gains in the building, then maybe around 4 air changes per hour will be necessary to keep you could say have an efficient nighttime ventilation. If you have medium heat gains, then you can see then the necessary flow rate increases a little bit. Maybe you need something around 6 air changes per hour to get an efficient night cooling. And you can also see that if you only have you could say, here's the green one, if you only have a lightweight building, then even if you have night cooling, you are not able to keep temperatures during daytime at an acceptable level. And if you have high internal heat gains, you could see the airflow rate increases even more. Maybe you have to have something like between 6 to 8 air changes per hour to keep the temperature in an acceptable level. And it's impossible in a lightweight building. You need to have a medium or heavyweight building actually to be able to utilize and to you could say remove enough heat gains during daytime. So nighttime cooling and ventilative cooling, depending on the heat gains, it requires thermal mass, and it requires a high flow rate during nighttime. The summary of my presentation. I think ventilative cooling can be a very efficient solution for both mechanical and natural systems. There are different challenges using either of the system. I think even if high summer temperatures might decrease the potential in summer, I think the development we see where we have a cooling need more or less all year round, even in residential buildings, increase the potential considerably. For cold climates, I think it's important for us to look into systems where we are able to actually supply quite cold air, so we can decrease the amount of air we need to transport and decrease the energy use. And then, of course, we have to look into how this system can be integrated with other systems. How should it perform in relation to solar shading? How should it perform in relation to mechanical cooling systems, which can be air-based or water-based systems for the periods of the year where outdoor temperatures might be too high or we have too humid conditions. At the moment, as you can also see in many of my slides, there is an international research activity going on, IEA EPC Annex 62, and we have a website together with the platform for ventilative cooling. So here you can see both results or information more related to, you could say, to the research part under Annex 62, and you could say information regarding the application and the more practical use under the Venticool platform. We are starting to improving as the project is going along. We are adding more and more information to the website. We have started to build up a database of examples of buildings, and we will in a few weeks also upload more reports and articles and so on about the use of the technology. So this can be an important source of information in the next in the future. Yes, thank you very much for your attention.
Thank you, Per, for this nice presentation. I think we just have one question here from Andre. Let me see here. It was related to the low and high and medium gains you are talking about. So I think he's asking, so how much does low, medium, high gains mean approximately? Do we have some numbers?
Yes, I do have some numbers. And actually, if I just get 2 minutes, then I can give the exact numbers. The low gains was 13 watts per square meter. The medium gains was 19 watts per square meter, and the high gains 26 watts per square meter. And that is, of course, the internal heat gains.
Yeah.
In addition to that is the solar gains.
Yeah, of course. Okay. Thank you, Per. And I think Kate has also a remark here. And that's related to the perforated ceiling and how we can cause. See here how we can allow. Just have to read it. There's something in front of it. So. How we can use perforated ceiling, allow you to supply cold air without causing thermal discomfort to the occupant. So how we can do that, and I think also in a few weeks from now, we actually have a webinar regarding this supply of cold air, just using this principle. I'm not sure if you want to put more words into that, Pierre, or we should take it in the next webinar.
Yes, we have another webinar later on diffuse air supply through diffuse ceilings. You could say the example from the Videx building, we did not use -8 degrees because you could say you only supply the air temperature at you could say that it fits to the cooling capacity. Because you have the minimum airflow rate is the one you need for indoor air quality, and then of course do not supply an air temperature lower than what is required to also keep the temperature. So I think the reason I showed with the -8 was just that we have tested how far it is possible to go, and our system was not able to provide temperatures lower than -8, and even at this temperature the system performed well. So, but I will explain more about it on the webinar in a couple of weeks.
Yeah, and I will also give you. I can show it now here. So I think it was the 24th of November. We have the webinar about diffused heating supply, which also Per will tell you more about. And yeah, of course, you can also sign up to this, and that's in around a month from now. So you can hear more about this system if you want to sign up for this webinar as well. Okay, and also we will of course send your presentation to you all, of course, if you want to, but I will distribute them to all of you after we have finished this. So I think I will distribute them tomorrow. Okay, but I think, thank you, Per, for this nice overview, and then I will take over and show you some examples, or some more examples, on how we can use ventilative cooling in the buildings. Just have to go here, like this. Yes, so I will tell you some more about the case studies. So ventilated cooling have been used in several buildings, both that's office building, and there could also be dwellings, as Per mentioned and showed. It could also be schools, and actually also shopping center, where we have these large atrium in the middle. So there's a lot of different building types where we can use ventilative cooling. So I will just give you some 3 examples. 2 of them are schools, where we have hybrid ventilation, and 1 office building in Denmark, where we have used natural ventilation, and I will just explain these to you as well. So if we start at the first one, this is called Mesterfjellet Skole, and that's located in Norway, actually in Larvik. And for those of you who are not familiar with Larvik city, then I can tell you that's around roughly 100 kilometers south of Oslo, if that gives you any idea of where we are located. Yeah, so this is actually the school building, as you can see here in the background. And here you can see I've also just taken some plan drawing. You can see there are different spaces. Some of them are classrooms, some of them are breakout spaces, and there are also some teaching areas and so on. So there are many different type of spaces inside this building. So when we look at the design of the ventilation system, so firstly it was proposed to use a full mechanical ventilation system with a capacity of around 19,000 cubic meter per hour. But after they have going into more details, they saw also a possibility to use hybrid ventilation instead, where they have a lower capacity of the mechanical ventilation system of around 50% reduction. So the capacity is around 44,000 cubic meter per hour instead of 90,000. So that means that they can reduce the size of the mechanical ventilation system with 50%. Also the ceiling height and the duct sizes can be reduced, etc. So actually this was the final design. They chose the hybrid ventilation system, where they have a smaller mechanical ventilation system and a natural ventilation system also. So if we look at some of the energy requirements in Norway, they have different types. They have what they call Tech 10, low energy, and passive house for a school building. And this school building was actually designed to around 90 kilowatt hour per square meters per year. So that would be in the low energy class. So what we have seen here is after 2 years, we have taken all the measurements from the heating, the fans, the lighting, etc. And then we can see actually what has been used during these 2 years. That's around around 60 kilowatt hours per square meter per year. So that means actually we can save around, in additional savings, you can say around 30 kilowatt hour per square meter, and the building is around 6,000 square meters, so that gives you a potential savings of around 190 kilowatt hours per year of savings. So actually it has been coming out better, performing even better than it has been designed. So I don't want to go into too much details with this one, but it's just to say that there's one system which controls both the ventilation, so that means it controls both the natural and mechanical ventilation. It also controls the heating, the lighting, and the solar shading. So all of this is actually implemented in one system. And also in this system, that's from Advanced, we call it, you can also have log data and so on to look at if you want that. So the reason why I explain that is, of course, we can do a lot of testing if you want to, because we have the full automation and the full control of these different systems. So actually we did a test during a winter time, so that was, I think, about the 14th of January in one a couple of classrooms. So we want to know, when does a classroom need cooling and when does a classroom actually needs heating. So this was actually the test. So now we are looking at some graphs here. So I will just take you through it. So the red, the red graph here illustrates the outdoor temperature. So you can actually see the outdoor temperature during this January day is around minus 19 degrees. There was no rain. The wind speed is actually illustrated here in green. So the wind speed is approximately in between 0 and 1 meters per second, so that's quite low. And the wind direction is, of course, changing during the daytime. So if we go into this classroom and look at some of the key performance indexes, of course, the CO2 is always very interesting. So here you can see here's the CO2 level. So here is actually at 5 o'clock in the morning. There's no occupant, so the CO2 level corresponds almost to the outdoor CO2 level. So we can see here the CO2 level starts to rise around 8:30-ish. So here you can see actually the people enters the building, where after the CO2 level rises to around 1100, 1200 parts per million, and then it goes along during the day. The same goes for the indoor temperature. It's quite stable, and then suddenly it drops, and then it rises again throughout the period. So why does this appear? So if we look at the opening of the windows, so actually we try to see how much can we open the windows. So we can see here that one of the reasons why the temperature drops around 6 o'clock in the morning is, of course, we have a opening, we call it a pulse, where we open the window for 5 minutes, and then we then we flush the room and have fresh air in the building, and that, of course, causes a drop in the temperature inside the building. So again, here you can see here we have one more pulse around 8 o'clock, and then when the people arrive, we can see we open the windows more. So here the windows are actually open around 50%, and actually it stays open almost all the day until 4 o'clock when the people, or 2 o'clock when the people leave the room. Okay. So what about the heating load, or the heating inside the building, the thermostat? So we can actually see, of course, we open the window at 6 o'clock in the morning, the temperature drops, and then the system, of course, the heating system react on this, and you can see here starting to turn on the radiator. So we can see we open the radiator, the valve, around 40%. So you can see here, so that's how much we open the valve, and then actually when people arrive to the room here, you can see the heating is actually turned off again. So, and that's even though we have the windows quite significantly open inside this room. So during the daytime or after, when people have arrived to the room, we can actually see that there's no actually heating requirements inside this classroom, even though we have the windows open quite large degree. So of course we also have some backup from the mechanical ventilation system, and you can see that. So this is actually showing the positioning of the damper. So here you can see up here, so that corresponds to around 100%. So that means that the damper is fully open due to the fact that there is a high concentration of CO2 level around 1100 parts per million. And that can also be seen during the day where we have these peaks. Then the ventilation system, the mechanical ventilation system, will open for the damper in order to compensate for this high CO2 rate. And you can see that during the daytime here. Okay. Yeah, so actually we can see in a normal classroom, this is quite unexpected. We can actually see that even though it's quite cold outside and we open the windows quite massively in order to reduce the CO2 level, we can still do that and do not have to use the heating system in order to compensate for the losses we have here. So we just have a question here. Why not open the windows more rather than use the image to meet the needs? Yeah. Why not open? Yeah. You could say that actually we could open the windows much more. In this, let's see here, we have it actually here. So in here, of course, we actually only open the windows around 60%. We actually could open it fully 100%, but again, it's a little bit of a balance between, of course, as you also point out, or Andre point out, that we should not cause the risk of draft too much, because we should still be in a zone where we can allow the people not to feel too drafty for this particular matter, even though it's actually just a test. Yeah, you can say that when we open the windows 100%, that's normally we do that during the break time. So actually in the system itself, we can schedule when does these people have, or when does this classroom have a break. And when they have a break, we can actually see or open the windows fully for 3 or 5 minutes of time, and then of course reduce the opening again. So that makes much more sense here. Okay, thanks for asking. So yeah, of course it's now we have looked at the winter time situation. So that was around January over here. Also in Norway, they also get quite high temperatures, outdoor temperatures. So the black curve here is showing the external temperature. So you can see here during June, I think it is, there's around 30 degrees outside temperature. So actually it's quite hot also during the summertime. So I'm not going into too much detail. It's just we have taken some of the hottest day here, Wednesday, Thursday, and Friday here in June, and we can actually see that during the nighttime we will open the windows fully over here, and then actually you can see that the indoor air temperature decreases during the nighttime with around I think it's around 4 or 5 Kelvin compared to the day temperature inside the room. So that's also a way to use this ventilative cooling. So yeah, and we also have a statement from the principal that the hybrid ventilation works very satisfied, and so on. So that's always quite nice. So I think I will move forward to the next one. That's actually a courthouse in Copenhagen, located in Denmark. So it's actually a courthouse, but there's also, of course, offices in this courthouse. So yeah, this is actually the building. So the building has a large atrium in the middle here, which of course we use for the natural ventilation, but also it has facade windows. Okay, and I will just go through that. So of course when we look at the ground floor and the courtrooms, these are all mechanical ventilated because they don't want to open any openings to the external environment, because then people can listen into what is going on in this courtroom and so on. So actually all the courtrooms are located in ground floor level, so that's around this area down here, and these are all mechanical ventilated, of course. But if we go to the upper floors, then most of them have a natural ventilation system, so that means that they 100% are reliable on the natural forces. So this is actually the plan drawing on to your left hand side here. So that's the plan drawing. You can see here is the offices. In the middle here we have the atrium. So what they do here is actually they have a facade window which lets in the air to the office spaces. Then they actually above the door have another vent which is letting then the air into the corridor, and then from the corridor into the atrium, and then from the atrium out. And I will just give you a brief walkthrough to this building. So when we look at the facade here, so here you can see actually the windows here is used for natural ventilation. Actually this one up here is actually open, so this means again this is how the air enters these office spaces behind it. So actually the next picture here shows you, here you can see the corridor. So here are you in the corridor, and here you can see actually this vent is open to when the door is, for instance, closed, we open this vent automatically, and then we would let the air from the office spaces into the corridor itself. And here on the other side you can actually see some larger openings into the atrium. So, and these actually also is, you can see there's a built on a chain on these openings, which allows the air to flow from the corridor into the atrium spaces. So here we are at the bottom of the atrium spaces, and here you can actually see these windows from the corridor, which actually can be opened and then allow the air to enter the atrium space. And in the top of the atrium space, you can see that here, we also have quite a large number of windows which can be opened, and then all the hot air will get out of these windows on both sides. There's also some windows here on the other sides. So this is actually the ventilation principle in this building. So actually we can also look at some temperatures inside the building during a summertime period. So actually again we can see here the green line or the green curve here illustrates how much we open the window. So actually you can see here where we open the window 100%, that's during the nighttime. So actually during the nighttime we use nighttime cooling, and you can actually see here from the red line we can actually cool that building down with around 5 or 6 Kelvin compared to the daytime temperature. Yeah, and then we can look at some snapshot of the indoor climate that's related to CO2 levels during wintertime, but also during the summertime, where we can see that we have some nice temperatures. I just want to go forward to this one. So here we can actually see this graph shows you the number or each different zone in this building. So that's on the x-axis down here. So one number here represents one zone, one area inside this building. And here we have the number of hours on the y-axis. So the blue bar represents the number of hours above 26 degrees inside this office space, and the orange one represents the number of hours above 27 degrees inside this office space. And in Denmark here we have some requirements that the number of hours should not exceed 100 hours above 26 degrees. So that's represented with this blue dotted line, and we should not have more than 25 hours above 27 degrees, represented here with this orange dotted line. So actually you can see that regarding the 26 degrees, none of the room exceeds these 100 hours during 1 year above 26 degrees. Actually, when we look at the 27 degrees requirement, we can actually see that there are one zone here which exceeds that with 1 hour, and another one with here with 3 hours actually. So I think we can still say that this meets the requirements. So yeah, then we have a nice statement here from the head of the administration, and he's very happy with this system. So I think I will just move on to the next one because I can see the time is running out. So this is actually another school building, actually here in Denmark, where we have a hybrid ventilation strategy solution called FutureVent. So actually you can see this is back here we have the school, we just have a hello, is it the 100 hour within the occupied? Yeah, so it's the occupied hour. So it's not a 24-hour schedule. It's only where people are actually inside the building, so the occupied hour. You're welcome. Yeah, so actually here we can see here in the back, the yellow stones here is actually the old building, and they want to extend the old school with a meeting hall and also some classrooms actually. But actually the ventilation system, the mechanical ventilation system, the old one could not be extended anymore, so they have to find another, of course, ventilation solution in here. So if we go to the meeting hall, this meeting hall is actually natural ventilated only. So we have facade windows down here and in the other side. And also we have some skylights, some roof lights in the back of the room. So we do not need mechanical, or we do not have mechanical ventilation inside this room. But if we go to the classroom then we have what we call FutureVent, and that's a combination of natural ventilation and mechanical decentralized units located in the actual construction up here. You can see this. So actually here we have the mechanical ventilation system up here, and down here you can see we have the 4 windows for the natural ventilation system. So yeah, so you can see this is from the inside view, and here is from the outside. So you can see here we have the openings from the outside, but also here you can see that behind this screen it's actually the mechanical ventilation component as illustrated up here. So actually you can see it's almost non-visible. So yeah, and then we have a lot of different strategies. So of course, during the winter time, we will primarily use the mechanical ventilation system up here with a heat recovery, a large heat recovery efficiency. During the summertime, we will mainly, or in the shoulder season, we will mainly use natural ventilation. And if we have, of course, a situation where we are not in the summertime, where we not can use natural ventilation due to the not so much outside wind, we can actually turn on all these mechanical ventilation units and make these as inlet, and then open the windows a little bit and make these as exhaust only. So yeah, this is a unit. If you are more interested, I can tell you more about this, but there are some fans inside it, there are some heat recovery units here, and there are some internal and external grills as well. So actually we also have some log data for this building type. So actually we have some CO2 levels during the winter time, and also some temperature curves during the winter time situation. So yeah, we can monitoring this at all time and see if they comply with the guidelines as well. Yeah, and then we have some statements again from the caretaker, and he is very happy about this system as well. So just to sum up very briefly, so actually we have some case studies that show that ventilative cooling can be a very energy efficient solution, and that's of course both mechanical, natural and mixed mode system, which I'm talking about here. We have some log data regarding the indoor environments, which actually we can see we comply with the building codes, and also we can see that as Per also mentioned, that the that the cooling demand is not only occurred during the summertime, but it can also actually be during the shoulder season, and to some extent also during the winter time situation. So before we go to the Q&A session, I think we already have discussed this a little bit, but I just want to say that on the 24th of November we have this webinar where Per also will speak about the diffused ceiling supply, and how we do that and how that can be done actually. So I think that was it from now. of course, now we have the Q&A session. I think we have 5-10 minutes left. And of course, I will send you the presentation anyway, so you will have them. And if you have any questions, of course, you are more than welcome to contact at least me. Yeah, you have my contact details here. And I think also you can write a little bit to Per if that's okay with him. But yes, if you have any questions or anything else you want to share with us, yeah, you're more than welcome to ask these in the chat area. Yes, yeah, thank you all, at least, for listening in, and hopefully you can use this in the future. We will just hang on a few minutes to see if there's some questions. Thank you, Richard, for that. Yeah, and as Pierre also mentioned, on the EA Annex on the Venticool homepage, Pierre will also have some more project cases, and there will be, of course, in the future, you will have the possibility to look at much more project with ventilative cooling if you want to look at that. Yes, we have a very nice question here. So what airflow do the mechanical ventilation units deliver? So actually, these can be designed in various sizes. They can also be stacked, actually. I'll just go back here. Just to give you here. Let's see which one is the best. Yeah, so here you can actually see that you can actually have different sizes of these. So depending on your need inside your building, you can actually have 800 cubic meter per hour, you can have 400 cubic meter per hour. You can so here you can see these are actually just in one row, in one line. So actually we can also staple these on top of each other if we want that, and that can of course provide you more air into this space. Yeah, of course there could be a condensation problem or something that you have to consider. I think Philip asked to specific this solution perhaps. Yeah, so actually what these units does is of course they rotate. I think I have it here. So they work in pairs. So the one that is, yeah, you can see over here on this side. So firstly, these two units work in pairs. So this unit will bring in air and the other one will exhaust the air. And then the next moment, 1 or 2 minutes later, depending on the conditioning inside, this unit will actually be the exhaust unit and this will actually be the inlet unit instead. So of course the condensation will be to some extent, but then we have this slope of the unit which actually can make the air and the water run out of it. And then we have Arne who asks, do the MV units need filter maintenance? Actually, there are, in this project case, there are no filters inside the unit. Actually, you can have a filter, but there will be an electrostatic filter inside this unit. So this should be thought about, that if we can use natural ventilation, then we can also use this unit, because normally we don't have the filters inside these systems actually. I think Arne is writing. Okay, thank you. Yeah, you're welcome. And actually, we also have a webinar on our homepage regarding this future event. So if you're more interested, we have recording of the latest webinar of this future event, both in Danish and in English on our homepage, if you want to hear more about that. Yes, I think, now the time is around 3 o'clock, so if there's no further questions, then I think we will say thank you from now. And Per, are you still on?
Yes.
Yeah, I will also say thank you to you, and thanks for the nice presentation.
You're welcome.
And hopefully we'll see some of you again on the next webinar. And if we are not seeing each other, then you will have a nice day. Okay?
Bye.
Bye-bye. Bye.